Hello, I'm Carolina Figueroa, and this is Lab 3, Magnetic Field of a Bar Magnet for Physics 2212. The purpose of this lab is to measure the distance dependence of the magnetic field due to a bar magnet, calculate the magnetic dipole moment, and compare measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields. The results from my lab were that the distance dependence is equal to negative 2.9933. The magnetic dipole moment is equal to 2.1403. To take the measurements for this lab, I downloaded a magnet meter app. I used a Tesla meter for iOS, there's a screenshot. To compensate for the presence of the Earth's magnetic field, I placed my phone on the table and rotated it until the X component of the app read as close to zero as possible. I went outside to collect the data. I made sure the B net was as close to the value determined by my latitude and longitude, and then I aligned the measure tape along the bottom of the phone so it ran east to west. Then I had to find where the magnet meter in my phone was placed. Then I had to find a distance from the magnitude to the sensor that produces the magnetic field with an x component of magnitude Bx equal to 20 megateslas. I will call this distance R20. Bx will be recorded on the spreadsheet provided for us, and then I will repeat this 2 more times to find an average. I repeated this process for R70, R120, R170, and R2020. Then I found the distance dependence from this equation in the Excel spreadsheet. The physics principles used in this lab were the Biot-Savart law, the distance dependence, and dipole on axis. I included the equations here. The assumptions for this lab were that the x-axis as defined by the magnetometer app points along the width of my phone, the y-axis points along its height, the z-axis points out of the screen, the net magnetic field in Atlanta, Georgia is 49 megateslas, and R is equal to 1. The observations were that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. A bar magnet is the magnetic dipole, and Earth also acts like a bar magnet. Here is the data for my experiment, including the graph and the off-axis data. These are my calculations. I started by calculating the distance dependence with the equation V bar is equal to K times R to the power of N. Using that equation, you can find N the distance dependence and K a constant with the following equation. I found N to be equal to negative 2.9933 and K equal to 4.2 times 10 to the negative 7. I found V bar to be equal to 4.28 times 10 to the negative 7. I used that to find the magnetic dipole moment. In this equation, I was solving for mu, and then I found mu to be equal to 2.1403. Here is my GlowScript code. I began by creating the magnet at the origin. Then I found the magnitude of the magnetic moment, and I created a function for the magnetic field. Then I drew 2 arrows to represent the magnetic field on axis. These arrows will be shown in orange. Then I drew 4 arrows to represent the magnetic field perpendicular to the axis. These arrows will be shown in blue. Then I went on to do the 45 degrees off axis. I began by averaging the perp for my experiment, and then I drew an arrow to represent the magnetic field 45 degrees from the axis. This arrow will be purple, and then I found the magnitude of the magnetic field 45 degrees from the axis at distance d. Here is the computational model from my code. This is the off-axis results. I found the B-net of the measured 45-degree value to be 2.1998 times 10 to the negative 5 teslas, and I found the B net of the computed 45-degree value to be 2.2059 times 10 to the negative 5 Teslas with a 0.277% error. The reflection questions. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? The magnetometer would have been skewed in the magnetic north direction, and the values found, K, mu, and N, would have been inaccurate. What if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? The direction of the magnetic field wouldn't change, the magnitude of the field would approximately double.